Welcome, everybody, to the Innovators in Analytical Chemistry Education webinar for May. I'm Michelle Kovarik. I'm the chair of the Education Committee for the ACS Analytical Division, and I co-organize this series with Bhavik Patel from the University of Brighton, who I think is going to be unable to join us today. I'm really excited to announce today's speaker, but before I do that, I'm just going to put in a quick plug for our June webinar, which will be with Gunnar Schwartz, who wrote a recent paper titled Quantitative Analysis Experiments for Students, a literature survey from analytes to assessments, talking about the variety of experiments that students might do in that course. And that'll be on June 25th at the same time as this webinar with Gunnar Schwartz from the University of Bern. But today, I'm excited to welcome our webinar speaker, Professor Dr. Endler Marcel Borges. I'm probably going to not do justice to the name of his institution since I don't speak Portuguese, but he's at the Universidade Regional de Blumenau and is also the lead associate editor for manuscripts in the Journal of Chemical Education about teaching and learning analytical chemistry. Rather than take up any more of his time, I'm going to turn it over to him to talk about using LLMs for chemometrics. So, welcome, Dr. Borges.
Many thanks, Michelle. Many thanks. Welcome, everyone. And today we're going to talk about of some chemometrics. Um, I have sent to you a file where we have some data sets that we can work today. I will also talk a little about Jamovi. I have published in the Journal of Chemical Education two papers using Jamovi for basic statistics. Now, today we are going to speak more about statistics, and it is the kind of statistics that we pretend to share with your students, your undergraduate students. As I have been talking with Michelle before, in Brazil we have much more health science students nowadays, um, and this course was thinking for the undergraduate of any area like a chemistry engineer, but we have some focus in health science students. The first data set that the first data set that I have the first data set that I have chosen to show for you is the Palmer's Penguins data set. This is a very known data set for this is a very known data set for chemistry teaching, for teaching statistics. So we have, you might open this spreadsheet in Jamov. Jamov is a free software. The Jamov is a free software. You might get and use it for free. And we have been using it a lot because when I began is with the statistics, I believe that everywhere when they graduated were not accustomed with R language, Python to code. Most of the students were not familiar with coding. And for to be sincere, I have been coding since some time ago, 2 years ago. Uh, so I can say that coding is not common. Most of your students will be not familiar with coding. So this program is totally written in R language, but the difference from him from the R Studio or the R program, the R package, is that we can use a graphical user interface. You have a graphical user interface, and you can work statistics without to know anything of code. Later, I will tell case history that we might use large language models like ChatGPT, Gemini to teach how to make some codes. Uh, uh, as I say, the main idea was not to teach coding, but is a very good assistance for coding. And as I say, since most of the people were not accustomed with that, we might, it's a good introduction. It's a very introduction tool. So I will present to you the Palmer's Penguins data set. Uh, as probably most of you know, we have qualitative and quantitative variables. So this data set talks about the Palmer penguins that was published, a data set that was previously published. For example, we have in here, we have the student name. That's we have it might be we have three discriminations of your variables using Jamovi. You have the ID, that is the name. For example, you are working with students. It's a table that have information about the students' ID, name, or if you're going to do any mal student, you have an ID for each sample. It's for just for you identify your samples. So, and you have the quantitative variables. Quantitative variables is like we have in here the Coulomb length, the age, the flipper length, everything that we can measure with numbers is say that is a continuous variable. For example, your age, uh, your size, it's everything that we can measure using quantitative variables. That is, we can measure using quantitative numbers. And we have qualitative variables. For example, your sex, male, female. Uh, in this case, that we have the Palmer penguins, we have two qualitative variables: the sex of the penguins and the species. We have three penguins species. So we have it as qualitative variables, the species and the sex. And we have some quantitative variables like the Coulomb length, the age, the body mass, uh, and the water, and also water variables. Well, when I begin the statistics processing a data set, well, the first step is always uh, to make a descriptive statistics. In the software, you might do it easily. You just can go to Explore and Descriptivities. In here, I will select the variable that I must work, a quantitative variable. For example, I will look for the body mass of the Palmer penguins. Here I have the number of observations. Uh, there is two cases that the body mass was not measured, so the software say to me that I have two missing values. I have the median and the median. Uh, um, the standard deviation, the minimum value, and the maximum value. I can go to statistics. We are in here, and I can choose the parameters that I will provide about my data set, my quantitative variables. So normally I don't think that maximum and the minimum value are something that I should report. The standard variation is important. Uh, uh, the number of observation, missing values, mean, median, and so on. And they have some parameters like the Shapiro-Wilk. This is about sample distribution. Normally, in undergraduation course, the students, when we make some statistics with the students, we just talk about the normal distribution. So the students think that our data is normal. No, but we have data sets that were not normal. For example, in health science, if you're going to look for the concentration of a pharmaceutical in the blood, most of the time it is log normal that have a log normal distribution. So, so the students must know that the data set might be a normal distribution, but this distribution might not be normal. And even we have a normal distribution. The students see in the books the beautiful Gaussian curve. You put it in the half and they have the two halves exactly the same. But in true life, we don't have this. And I believe that words worth more than 1,000 words might be what you can be teaching with plots uh, might have more value than several tables and other things. So we have some basic plots in here. The first one that I'd like to work is the histograms. We have the histograms in here. For example, we have in here body mass. As you can see, it is not a perfectly Gaussian. Uh, we have the tails. So these tails and when these tails that we have, we can call a symmetry, might be evaluated by skewness and kurtosis. And we might add in this. We can see that we have you can see here that we have a right detail in the data set. You might do it also. We have in here split by. In here, we might add your qualitative variables, for example, sex and species. So I can see, for example, how was the body mass for males and females? How can I do it? So we might add here your qualitative variables. For example, we have sex. I believe that there is one sample that was there is a point something and was classified as another class, but we have just males and females. You can look to here. We have done the histograms for males and females. When the data was splitted by males and females, the first thing that we can see is that the distribution have a bimodal function. We have the data sets is bimodal. We have a bimodal distribution. And we can see clearly that the males might be a large mass than the females. So another kind of plot that I like very much to compare your data sets is the box plots. So you might do a box plot comparing male and female mass, as you can see in here. And you can clearly say, you can see easily for the box plot that males have a large mass than females. Uh, for example, when I was in my graduation, and when I get the graduating course in the State University Campinas, we have to do a statistics course, basic statistics. But at my time, all the statistics was based in hypothesis tests. So our comparisons that we did, it's very important since we're going to do any kind of research. You have to compare the two groups. For example, I'm analytical chemistry. I am comparing the concentrations in different groups, or I am comparing different methods. I always have to compare the two or more groups. But everything that I see in my undergraduate and the graduation courses is hypothesis tests. So I never have idea. Well, I just look for p-values. No, we have a lot of things that can give you a better information than just p-values. Uh, Something that we talk in the end of the of your meeting is that sometimes normal and the non-normal hypothesis tests give different results. So, and if you are going to consider your non-normal data set as normal, your hypothesis test will provide the wrong p-values. For example, you conclude that the two groups were different, where in truth they were not, and the same is valid. So, what is the first information that we get from those plots? We can see that when you compare the penguin's body mass The distribution is clear, no normal. You have a bimodal distribution. So your data set was not normal. If I am going to do any kind of comparison, I should not use normal tests. For example, the well-known the t-test. And looking for the histograms, I can say that the males might have a bigger body mass. I look to the box plots, I also can see that males have a bigger mass than females. I can look for another qualitative variable. For example, I might use now the species. Now I am dividing it by the species. So I have three kinds. I have the three species in here. I have the Gento, I have the greenstrap, and the Delhi. As I can see, these two have a very similar body mass. And this one that is the Papua penguins, they have a larger mass than these two. I believe, as I said, looking to a plot, you have much more information that you can take it from just, for example, to do one away ANOVA and later the post hoc tests. It is clearly shown to you that these two have equal mass, equivalent body mass, and this one have a larger body mass. Looking to the box plots, you can also the same thing. I like very much to compare my data set using histograms and box plots. The great advantage of box plots is that you can see the outlier samples. That just samples that are much larger than the median or much smaller than the median. Uh, they you be they will be clearly showing here, and you can see the outlier samples. So you can see the outlier samples. You can see both qualitative variables at the same time. For example, I might see species and the sex at the same time. For example, I can put the sex in here, and now my plot will be divided by sex and species. So in here we have the a plus here. So you can see in here we have the Adelie penguins. Always the male is heavier than the female, as you can see in here. And uh, we can also see the penguins that have a larger body mass. It is good showing here. We have in here a box plot. So in here we have the green is the females, and this light orange were the males. So we can see that Papua penguins were the bigger ones. The female Papua penguins will be larger than even the males of the other two classes. Uh, so what I pretend to show for you now. Well, looking to box plots, you might compare more than two qualitative variables at the same time. You can compare your groups, but if you have more than one qualitative variables, you might compare both at the same time using box plots, for example. Uh, Normally, if you are going to compare just two groups, we use a t-test for normally distributed data sets. For example, I like Jamovi because it is very illustrative. So I already have shown that the males have a larger body mass than the females. Uh, you can do it using hypothesis tests, looking for the p-value. You might look in here, for example, I can choose my dependent variable, that is my quantitative variable, and then here you put body mass. You can put the body mass in here, and later uh, you can put in here the qualitative variable, and they are going to make the calculations. Well, I believe that it don't work with this data set because I believe that some sex in the data set was writing wrong, and they think that is three classes instead of two. Is a curve that you have to take. But anyway, we can do that. We can do that for another data set that I have here. But well, we have it in Jamovi. We have three. We have a parametric and non-parametric tests. For example, we see that your data set was not normally distributed. Your data set was not normally distributed. So the non-parametric version of the t-test is the man-Whitney test. So it is more indicated in this case, you use a non-parametric test than a parametric test. And then when you have to compare more than two groups, use one away another. One away another is the case when you have is the case when you have more than two groups. For example, we're going to compare the body mass. We have to compare body mass, and in here we have the variables. So we are going to compare body mass between species. So we're going to put these species in here, and he calculated the p-value. For example, in one away another, when you have a p-value that is smaller than 0.05, you say that you have a difference. But the Jamovi just calculate like this when the p-value is much low, very small. So if you're going to do hypothesis tests, your one away another should have shown that the body mass are different. But where is this difference? You make it, you have to compare more than two groups. Well, I do one away another. Okay, I do one away another. And the one away another had shows me that the groups were not equivalent. But where is just difference? Well, we might look for just difference using pulse hoc tests. Uh, right in here, you might mark, and you have some pulse hoc tests. Jamovi has the option. Jamovi has the option to do two kind of pulse hoc tests. We have the Games-Hauer test and we have the 2K test, where probably the 2K test is the most used. The 2K test is the most used pulse hoc test, but it is very sensitive to different variations. If the samples that you are comparing have the variances that is different, the 2K test is not a good choice. The Games-Hauer test is more appropriated when you have groups with different variances. So we see that the three groups were different. I already have shown this for you using histograms and box plots. Now we are going to see where we have just differences. So we can begin with the Tukey test. If you are seeing Tukey test in here, you are going to see where the differences are. Oh, I cannot scroll my bar. Oh, now we can see that, uh, well, we can see that, well, I have a trouble to scroll my bar in here, maybe because my presentation is open. But you can confirm it using the post hoc test, what I already have observed in here using the box plots. Now we can confirm this. Uh, in this case, since the data was not normally distributed, we might use a non-parametric option. Well, I have used now a parametric option. And a way another is used when you have a normally distributed data set. When you have a normally distributed data set, you use an array and all. But if your data was not normally distributed, you might use a non-parametric option. This non-parametric option is the Kruskal-Wallis test. So we can go to Jamovi, and you have ANOVA, um, and you have a key, and you have in here non-parametric options. So we might go to the Kruskal-Wallis test. You go to the Kruskal-Wallis test, and they're going to do the same. You put the body mass, and then here I put my qualitative variable, that is the species. Well, the Kruskal-Wallis test gives me the same result as my parametric test that's on our way and off. The three groups were different. Okay, the three groups were different. And now I can use a post hoc test. I also have a post hoc test for non-parametric data. That is the pairwise comparison. We have a complicated name here, but in here we can say the same thing that you observed using histograms and box plots. We can see that Adelie and the Antarctica penguins has the same body mass, uh, where while the Christmas, the Queenstrap penguins have a different body mass from the Adelie. No, sorry, it's the Gento. It's the Gento penguins have a large body mass than the other two. And we can confirm this using hypothesis tests. Uh, when I begin my presentation, I said that in my graduation and undergraduation, we look too much for p-values. We have to compare three groups. Normally, we have much more than three groups, but the best example is three groups. Now we have to compare three groups. Well, but let me do one way another. Oh, I have a p-value that is smaller than 0.05. So the groups were not identical, it's not equivalent. What they can do now, now we're going to do a post hoc test to see where the differences lies. No, it's a good option. It's a good option to do this using hypothesis tests. But much of the time is you do not look for what was happening. So I prefer to illustrate that for my students through the histograms and the box plots. I prefer to illustrate like that. Uh, and the first thing, when you have your data set, look for the normality. For example, you must look if your data is normally distributed because you have to use parametric and non-parametric tests. If your data was not normally distributed, you have to use a non-parametric tests. But we have a great trouble. I see that most of my colleagues and all my students do not know that normally we have a hypothesis test to check for normality, the Shapiro-Wilk test. Oh, let me see. Let me see if the body mass was normally distributed. I get back to descriptive statistics. You go to body mass in here, and I don't do split yet. I just let the Shapiro-Wilk test. Let me see with the what the Shapiro-Wilk test say to me. Now I have put the body mass. Well, I have it. Oh, Shapiro-Wilk test said to me that my data was not normal. But you must take in mind that Shapiro-Wilk tests um, was prepared for small data sets. If you have a large data sets, he's very sensitive. And sometimes you have a small departure from the normality. You see clearly that that is a normal distribution, but we have very small p-values for the Shapiro-Wilk test. You must keep in mind that Shapiro-Wilk test is very sensitive for large samples. Normally in chemistry, we don't have a lot of samples because it's very expensive. You have a sample analysis, so you don't have it too much. But must keep in mind that the Shapiro-Wilk test might be very sensitive uh, for large samples. So I prefer to illustrate it by histograms. Uh, I prefer to illustrate that by histograms. I can see clearly here. It might be close to a normal, but it is heavy skewed. It's a heavy skewed data set. Now, so as I said, an image is worth more than 1,000 words. So this is the first data set that I bring to illustrate it for you, how you can use Jamovi. Normally, we have to compare two groups or three groups in chemistry or health science, engineer, and STEM applications. You can do by hypothesis tests using here. It's very illustrative. And here, we have three groups being compared. Normally, we have the as a normal test. We have the t-test, and for the normal sample, we have one away and all, and we have one away and over here, and we have the non-parametric options in here. So begin doing a histogram, see if your data follows a normal distribution. Then you might choose if you are going to use parametric and non-parametric tests. Well, after that, we have we have shown the first steps in data analysis. Well, another option that I always teach in my chemistry classes is the principal component analysis. Why principal component analysis? Because you can see relations between the data set and you can see how the data set was grouped. So uh, we have this option here in Jamovi. You can do principal component analysis in Jamovi through this option. Well, you might go in here and you look to principal component analysis. Well, in here, I put my variables that I use to differentiate the penguins. And I can put in here the column length, column depth, fliper length, bond mass. And in here, I can put the class that I want to separate. For example, I can separate the Palmer penguins according to their species using just choose four variables. Well, I go to this option, and I have in here the graphical options. I choose to scale to unit variance because when you work with continuous data, the variables that have large numerical values will dominate it if you don't use this option. Remember that when I was in my graduation course, I have a conversation with another guy that he works with Chemometrics, and we say, every time that you do principal component analysis, you must autoscale your data. Well, if you are working with continuous variables like that, you have the Palmer penguins and you have the four continuous variables, quantitative variables, column length, body weight. You must use the scale to unit variance. You must auto-scale your data set, or the variables that have large numerical numbers will dominate the principal component analysis. But when we work with spectral data, for example, I have a friend now doing this. We'd like to differentiate the risks from different species. We take the risks and take the Fourier infrared. They take the infrared from different uh, kinds of risks. So now we don't have continuous variables. We have specters. For a hash sample, we have a spectrum. We have the observance measured in different wavelengths. In this situation, it's different. But is well, we can talk this in another encounter, but it's very different. So you can use the principal component analysis to see if you can differentiate the Palmer penguins using these four variables. You can do principal component analysis in any data set that you have to see if it is differences and things similar in the data set. For example, the Palmer penguins data set. Can I differentiate the species using just four variables? You can do this just looking here. Well, I have to put a color. Uh, this is a trouble that we have with Jamovi. Uh, it is very good for descriptive statistics. It's amazing for descriptive statistics. But uh, you can think that for principal component analysis, it is a bit lazy. My computer is very powerful, and he's taking a lot of time to process. So if you are going to do to get to what we really knows as chemometrics, well, descriptive statistics might be included in chemometrics, but normally what someone to say, I teach chemometrics. We are more might talk for supervised and unsupervised methods like principal component analysis, partial least square regressions. So, well, in here you can see the separation between the Palmer penguins. You can say that we have a good separation of this group from this two. And this group, we can also see some differentiation, but these two groups, as I can see for the body mass, they are close. This one is easy to separate from these two, but separate these two using just these four variables is not something simple. So, for example, was invited to go to Antarctica to differentiate three different species of penguins. Well, using just four variables that I used, they can easily differentiate these species from this two. But to differentiate this from this, well, it's not so simple. I have some superposition of the classes. I like very much principal component analysis because we have the loading plots. The loading plot says the importance of the original variables through the new space. Uh, every time that I teach principal component analysis, I don't enter too much in the mathematical approach. Um, when I was a student, I tried to explain it is base transformation. People that were doing algebra uh, might be have some work doing base transformation, but well, it's mathematically complicated. We are going to it was not your objective today. But you can think that if you have two variables, you might be a normal plot. If you have three variables, you might do a plot yet with the humans can see in three dimensions. But if I have several variables, more than three, well, I have to do something to visualize my data. So if I have a data that have 10, 20, 100 variables, I will combine these variables in just two new variables. And I will project my samples through choose new variables. Of course, if I am comparing several variables, if I am merging several variables to have just two, I will lose information. Is this that we can find here? In principal component analysis, we have two variables, the PC1 and PC2, the principal component 1 and the principal component 2. We can see that the first component, we have a lot of the information. And then the second, we have a bit more, less. We have it transformed four variables in three. So we retained most of the original variability of our data set, but some was lost because it transformed four variables in just three. And in here we see the importance of the variables, the importance of the original variables in your loading plots. For example, samples that is in this size, in the right side, they have large coronal length, large body mass, and large flipper length. We can see that the Papua penguins, they will have the larger coronal length, larger body mass, and larger flipper lengths. Uh, the penguins that was in here, they will have the larger column depth. So we can relate the importance of the variables to differentiate the groups. Okay. Now I have prepared three data sets. I believe that we just can work with two today. I will open another data set. Uh, well, I will choose the browser what I have saved. I will open this another one. No, sorry, this is my COVID data sets, Journal of Chemical Education. It was a Journal of Chemical Education paper about about a COVID data set. And we are going to look to work with this one. Well, we have a wines from different regions. This is a wine data set. We have three kind of wines. We have the type 1, type 2, and type 3. This is a data specifically used for teaching. We have three kinds of wine. Was there any difference between this wine? How can I differentiate these three kind of wines? How can I do it? Well, the first thing that I'd like to do is to do the principal component analysis. So I have several continuous variables and just one qualitative variable, the wine type. So I put all these variables in here, and I put the wine type in here. And then now the Jamovi are going to produce to me the score plot and the loading plots. What Jamovi is going to do, he will merge all these variables to obtain just two new variables that were the principal components. And in here, I am going to see how was the distribution of my samples. Here, I must assign one to he do it with colors for me. Well, when the Jamovi was thinking, I'd like to briefly illustrate something for you. As I said, that Jamovi is good for descriptive statistics. If you want to compare one, two groups, please use Jamovi. But when you are going to Chemometrics, he just can do principal component analysis. And as I am showing here, I have a very powerful computer. We don't have a complex data set. It's not, it's a huge data set with thousands of variables. Uh, it was taking a lot of time for it to be processed. If we're going to work with spectral data, we have 5,000 points per sample. Certainly it will not process because he's lazy for this kind of stuff. So the best option is to use the R language. I just close this one. The best option is to use the best option is to use the R language. At this time, I believe that some of you are going to say, "Oh, I don't know how to code in R language. How can I do it?" Now, it is just a starting point. You don't know. I don't. Well, when I did it, I don't know anything about code. So how can I code in R language if I don't know coding? No, just a brief description. what you can do about it. Well, okay. Well, I will import my data set for a large language model. The best one, in my opinion, just my opinion, the best large language model or chatbot that you might use for assist you with this is Gemini. For example, I can go to here and send my archive for Gemini. Sorry, it went silent. I believe that it is one. Yes, is this one? Well, I uploaded my data set to Gemini. Now I will ask him what I want. We're going to ask him to do it. He was thinking. Okay, just take a look in here. Something happens in here. It was not generating my principal component analysis. Uh, I believe that I choose all the variables, and with all the variables, it gets very hard to him. Oh, sorry. I believe that I must put the types in here. Well, now he is going to think. Now he will process the data set, and we are going to see how it gets separated. But before Jamovi show it to us, you can see what Gemini did. Well, Gemini have done the loading plot, and he have done the score plot. You can see type 1 line here, type 3 line here, and type 1 in here. Gemini have done the principal component analysis for us. Um, he had shown the loading plot, so we can see that samples that were at this size, samples placed at this size, will have large hue values, dilution, flavonoids, protocyanins, and phenols, the wines that were in this part. And then some at this time are going to say, oh, well, how can I say that the results were not hallucinated? Yeah? How can I say that it was not hallucinated? Well, first, when you have a calculations, I don't have a lot of chance to have hallucinations. Some dangerous hallucinations, as a student asked, this substance, this compound, it hazardous? And the large language model says, no, it's not hazardous. Where in truth, it was very hazardous. But we just need it when asking large language models, chatbots to do this kind of stuff, uh, we must fix some parameters, like in a normal software. For example, I can ask, well, I must prompt in here. I can ask, what kind of pre-processing did you did? For example, some normally the large language models are very smart. They know that they are working with continuous data. So if it was a continuous data set, we have numerical values, it must be done using autoscale. So he make me a report in here, and he say me she was autoscale. Oh, I believe that everyone that was in this meeting upload this data set, and they ask, please build me the loading score plot. Give that to everyone in this meeting. And even if I have 1,000 people here, even if you have 1,000 people, you are going to get uh, the same plots. Why? Because the algorithms that generate principal component analysis are close related, very close related. And the large language models knows which was the best processor. I just have one kind of processing, data processing for this kind of data that is out scale. So here always be out scale and reproducing it. But for example, now we are working with spectral data. Well, there is many kinds of pre-processing methods. If you do not say, oh, I'd like this kind of pre-processing, uh, probably between the time that we have, for example, 100 people doing this meeting, everyone will upload the data set and just ask, please build the loading and the score plot. Certainly, in one case, the large language models are going to use a different data processing. So we are going to have different score and loading plots. Uh, and you have I have found a good manner to make your data traceability and reproducibility. At the end, you might say, nice, please provide me the scripts to reproduce it. You
Mike by
can
one
do
two three.
this. You can do this. And then I go to here and say uh, the path that was your file. And they'll go in here and say, my file is my file is in the path. Please generate a high resolution image in this path. Now here going to process. Now here is going to process, and you make the R scripts that we need to do it. Now he's thinking, and here is going to provide the R scripts, the codes. Well, if you do not know how to code, you have a good starting here. He explains everything. They say, oh, you need to load the choose libraries. You need to choose libraries to make chemometrics. Well, your file is in here, and so on. Give you detailed information. Let me see if you work. We're going to cope, and we're going to work program, and let's see if it work. Well, a high resolution image was saved in your directory. Well, I must see the path that we have saved. Let me see. Well, I can look for the paste now. Well, I just not find the place that it was saved. He's saying that it was saved in here. but I was not finding the image. I'll try that again. Let us see now. Well, I thought I am not finding where the image was saved now. Maybe you need just write it to do it again, but we are close for your time. But you might try to do it at your home. Load this data set, ask to do the score and the loading plots, and after that, request the R scripts. But you must say the path that was your file. I know what happens. I don't ask to generate in the same path a high resolution image. You must prompt this, and he will provide R scripts that will devolve that will generate your image, and they will get back R scripts that can generate the principal component analysis, the loading plot, the score plots. It's a good start for R language and how to code. You might try it at home. I'm sure that they're going to work. Well, we're close for our time. I appreciate very much the invitation done by Michelle. Many thanks for the invitation, Michelle. And many thanks for everyone that came to see and share with me. Many thanks to everyone.
Thank you so much. We have a couple minutes for questions if anybody wants to ask something.
Sure. Is it okay if I ask, Michelle?
Yeah, go ahead.
Claire?
Have you done any large language model sort of assisted image analysis? Like I know your recent paper on like using cell phone images in analytical analysis. Have you done any like AI assisted image analysis? And do you have any tools to
No,
recommend?
no. Image analysis, I don't do that because I like to use 96 well plates. When I work with digital images, I like it very much because you using digital images, you don't have any troubles with your metrics. In analytical chemistry, we cannot never analyze directly milk, but I can analyze milk directly using digital images. Right? Just take an image, uh, and I like 96 micro plates because you can analyze 96 samples at the same time. But I have a plugin from ImageJ. I have a plugin from ImageJ. It's from some guys of Argentina. Uh, I found it in ImageJ website, and I appropriated it. I have been using it a lot. Uh, why? It's good because this plugin take it the green, blue, red values at the same time. I just say him what is the last and the first well of my plate, and we extract instantaneously all the wells. So uh, now I am working directly with images. Well, it's huge trouble. You're getting all images out. Let me see the green, the blue, the red. Now, you just put the information. Where is my first and my last? Well, I just put this and he turned me all the values. It's very simple. But I believe that I don't publish. And I tried just a couple of times. I asked to the large language models extract the values to me. I believe that was pretty close from what I take from ImageJ plugin. Is the name of the plugin is ReadPlate. I have done a video when I began to publish this kind of stuff, working with digital images. I make a video, and the people from the Journal of Chemical Education say, no, no. You show a lot of logos of the American Chemical Society, uh, making something that was not directly related to the American Chemical Society. And I do a YouTube video. I have a video on YouTube showing how to extract red, green, and blue values from 96 well plates.
Okay, thanks.
Kim, I have seen a lot of publications of you, but I never see any picture of you. Now I say, where are you?
I know,
I
same
also,
thing. I was just telling my student who's joined me for this webinar, I was like, oh, he and I play in a lot of the same pools.
yes, I
So
also
it's
see a lot of
nice to
papers.
meet you electronically.
I have done also see several manuscripts for Michelle, but I never have seen it before, and I'm very glad to can see Michelle and Kim to see both of you. Now
Yep.
I can see where is these people that I have been looking to many papers. Now
Yeah,
I
It's
know
funny to see
the authors
someone's
of the
name so
papers that
much in your
I
email and not know their
read.
face.
Yes,
yes,
I also see yours.
exactly.
All right. Well, we'll wrap things up since it's afternoon now, at least on the East Coast. But thanks everybody for being with us. And thank you, Dr. Borges, for a fantastic demonstration of some techniques. That was really cool. I'll be sending out the recording and links to the resources that were mentioned today, as well as the registration link again for the June webinar, which will be Gunnar Schwartz talking about a survey of quantitative analysis experiments. So thanks everyone and enjoy the next month. I hope to see you later.
Many thanks. See you.
Bye bye.
Bye. All right. I'll close this up, but thanks again. It was great.
Many thanks. Many thanks. See you.